Right, so I'm going to talk about some work I've been doing on how we can simulate triple stars with binary C. This is work I've been doing with Rob over, I guess it's sort of faded in over the past year and a bit. And I guess I'll first motivate why we want to study triples with some highly technical graphs, which are not updating. So I guess I'll just come over here. So this is a plot of how many systems you have as a function of how many stars in that system, and we know that there are some singles, generally more binaries, and then it kind of tails off from there. This is a plot of how often a system will do something as a function of the number of stars in the system. If you add more stars, it can do more stuff. If you multiply these together, you get this thing, and I really couldn't work out what to label the y-axis on this. I was going to call it like interestingness or something, but that's just that's quite mean. Maybe I'll call it like how much I want to study these things. And the peak is between 2 and 3. So that's my highly technical motivation. So yeah, how can we use binary C to simulate a triple? The basic reasoning behind this is that in order for a triple to be stable, it has to be hierarchical. This is what we've mentioned before a bit, but it's a system in which you have a close binary with a relatively distant companion. In this case, relatively distant is usually a ratio of semi-major axes of about 5-ish. Depends on the mass, inclination, eccentricity, etc. So we can run a binary, or specifically two binaries, using the API that we've already heard about from Rob. And then we can sort of tinker with it a bit so that it treats one of the stars in the binary as itself a binary. So we run the API twice, and then we sort of pass data back and forth between the two systems to make sure everything stays consistent. Basically, at this stage, that basically just means the mass. And so we can run an example system of this. So here's a diagram of a hierarchical triple, and then we can sort of, just with this very, very simple initial configuration of binary C, you can get some evolution that looks like this. So on the left, we have the mass of the 3 stars, and in the center, we have the separation and the eccentricity on the right. And this has been evolved for 15 gigayears. And you can see as the stars evolve, initially you get the blue one evolves first because it's the most massive. You get a common envelope event, which is captured accurately. You see that the triple orbit widens at this case due to the mass loss. And then you get a binary merger as the middle star evolves as well. And then the eccentricity goes negative, which is just how binary C represents a merger. So you can see that we already get some of the interactions, but we need to add some extra physics to the cauldron of binary C, starting with dynamics. Let me move this window over. There we go. Tides, mass transfer, which is the big one, and supernovae. So we started off with the stability first. This is the condition I mentioned before. This is from Mardling and Orset paper. And you can just sort of plug this in and see if your system obeys this or not. The motivation behind this is this comes from the positionings of various resonances between the binary and the triple orbit. And if your separation is smaller than A out, then you're in overlapping resonances and you can assume it to be unstable. So when the system violates this, we assume you get some kind of unstable 3-body messy interaction. Usually this will result in the ejection of one of the stars. Usually it'll be the lightest star, but not always. We don't simulate this yet. At the moment, this just terminates the triple evolution because it's a mess. Ideally in the future, I'd quite like to do some evolution splitting here. If we can come up with some probabilities of which star is ejected and the remaining binary properties, then we could sort of plug that back into binary C and see what it does, which I think would be really interesting. Right, so the big three-body dynamics thing is the Kozai-Lidov mechanism, or Lidov-Kozai, or however you want to order it. This is basically a formalism for describing the way that angular momentum can be transferred between the binary and the triple orbit. The result is you get changes in inclination and eccentricity, particularly in the inner binary. And under the right circumstances, this can actually flip the inner binary upside down, which is interesting. But much more often you'll get it reaching very high eccentricities, 0.9, 0.99, 0.999. Yeah. The main feature of the Causalova mechanism that we have to deal with is that it can happen on quite fast timescales. So the timescale for the evolution of the orbits is, very roughly speaking, the outer period multiplied by the ratio of the two periods. So that could be a few outer periods, maybe 10. You have some mass factors and eccentricity factors in there as well. So while we could just use binary C's orbital evolution for this, it would just result in a lot of calls to evolve binary star for dt, or the API function, which would be quite inefficient because we don't need to recalculate things like stellar structure, or there's a lot of stuff we just don't need to deal with on this kind of timescale. This is basically how you implement it. You just take all these equations and you write them in C and you put them in, and it works. So this is an example using the exact same system as before, and we have some extra variables to keep track of here. Notice that before, when we went up to 15,000 megayears before we now go up to 0.1, that's because this evolution is just much faster, as you can see, and there's no stellar evolution happening on these kinds of timescales. Yeah, incidentally, this isn't particularly slow to run. This was a fraction of a second, but you can see the oscillations quite well. You can see the inner binary reaches some very high eccentricities, which will cause problems further down the line. You also get the nice thing that the outer binary precesses, so it just keeps rotating, but the inner binary librates. Doesn't have much effect on the orbit, but it's a nice effect. And you can see that the eccentricity variations are tied into these inclination variations as well.
Quick question, is all the tidal interaction already
no. So yeah, tides are up next. So we have 3 kinds of tides to deal with in a triple. The first and second kind are the standard binary tides. So the first one, which is called intra-binary, this is the effect of one of the stars in the close binary on the other. Binary C already does this. The next up I call intra-triple, which is basically the same thing, except on the outer binary. And then the third one is the one that's unique to triple systems, which seem to be going by the term tertiary tides. And these are caused by the changing quadrupole moment of the companion. So the idea being that when this binary system is sort of side on to the triple component, it's less distorted than when they're all collinear. And since this binary is changing on quite fast timescales, you can just pump a lot of energy into the envelope, which is then dissipated. This turns out to be the easier kind of tide to deal with, and Yan Gao and Kunming has done a lot of work on this, where he's just done simulations of all of this and condensed it into a nice, easy formula that you can just sort of plug in.
Yan said hello.
Oh. That's Yan's formula. So we have some more issues with the simpler tides, in that we have these extreme and quite fast variations in eccentricity and inclination. The eccentricity is what we care about. So here's a sample plot of eccentricity against time, where each of these points represents running the triple dynamics evolution once. And so we run into problems where we evolve the binary on longer timescales than this. So if we evolve the binary here, it'll run at a much lower eccentricity than its true value. And so we'll underestimate things like tides. And you can have some sort of kind of aliasing effects here, where you consistently run it at lower values than is realistic. And this can have problems if, for example, your eccentricity is high enough that you'll get Roche-Lobe overflow and pericenter, or a collision, as you can for very high eccentricities. And so we have to be a bit more subtle in how we treat this. And this is what I'm working on at the moment. And we're going down 2 different routes to tackle this, and we'll see which one works better. The first is we have these tidal evolution equations. We have these tidal evolution equations, and these are formulae for the various tidal derivatives, A dot, E dot, and omega dot, which is the spin of the individual star. And these are some prefactors times a big, fairly complex function of the eccentricity. So one way to do this is to sort of tabulate this function while we're doing not tabulate it, to calculate this function while we're doing the dynamical evolution and sort of store the data. And then when it comes to the binary evolution, we'll just use the mean or the integral of that. The other way is if we tabulate the data in advance, and then we can just look it up using recorded values of the eccentricity over time. So that's what this slide is describing. The problem you run into is that you have quite a large parameter space for these tables. As well as being a function of the eccentricity, these derivatives are functions of the ratio of the rotation frequency of the star and the orbit. So you need to include that in your tables. And so you end up with a 4-dimensional table, well, 5-dimensional table, which is not much fun. And these are the equations we have, and these are the bits you can average. Yeah, so that's what I'm in the middle of at the moment, and hopefully in the next few days we should be able to work out which one is the one to go for, the tabulation or the integration on the fly. I think that was all I had for tides. I'm going to move on to mass transfer. So these are, I've described mass transfer in 3 different ways. We have wind mass transfer, Roche-Lobe overflow, and I've classed common envelope as mass transfer because it fits neatly in the table. And while it might be slightly overstepping to say that we completely understand these for binaries, we do at least have treatments for them. We can simulate it. How much you trust it is another question. And so I've marked them all with a nice tick. When we move to triples, of course, everything gets a bit messier, as you'd expect, because not only can you have, because the mass transfer can now go in 2 distinct directions. So we have had 2 rows to our table. So in the first case of wind mass transfer from the triple component onto the binary, this is what I spent most of last year working on, and did a lot of simulations of this and then wrote a paper about it. So we should just be able to apply that straight away, which is quite nice. Binary to triple wind mass transfer, I've marked with a question mark, because I think in theory, it will start to depend on things like the speed of the wind. Because if you've got a fast wind, then you can assume it will remain spherical-ish. And so we can just apply the von de Hoyle accretion from the intra-binary mass transfer. If you've got a slower wind, or a wider triple perhaps, then you might start to see effects of the wind being shaped by the binary, which might be quite messy. And we've seen these simulations of nice sort of spiral winds, and spiral shells, planetary nebulae, and this kind of stuff. So yes, I'm not 100% sure how we're going to treat that. Roche-Lobe overflow, I have no idea about this. I've marked it with 3 question marks because I'm very, very, very uncertain about what we should do, how you could even treat this. I think we're probably not going to include this in this first version of the code. I'm not aware of any existing treatments of this.
I have seen a paper that at least calculates the size of the Roche-Lobe dependent on the phase of the inner binary.
Yeah, so you should, you'll have this problem where it's kind of like the tides, where the Roche-Lobe will depend on the phase.
Yeah.
And so you end up with this question of, I guess during the times where the Roche-Lobe is smaller, so the star is more overflowing, how much of the matter can leave the star in that time?
Yeah, it's how much indeed can overflow in that period of time.
Yeah, and then once you even worked out the sort of mass outflow rate from the donor, then you have to work out where the mass goes, and that's just another problem by itself. I guess in the case of relatively close binaries, you could probably argue you'd get a circumbinary disk. And then in wide binaries, maybe something actually not too far off a common envelope, a binary common envelope. But yeah, I'm really not sure. I've marked the square below it with cross-hatching because I don't think it really makes sense. Yeah.
How much do you trust the SVH research that has been done on this?
For which?
Triple to binary. I know that Simon Portugues-Zwart, or one of his students, had a paper out
For winds or for
no,
rush
slope.
Yeah,
onto the inner binary.
I'm not sure. So the problem, well, you run into the problem of it seems like it should be quite disky, and I do remember seeing these, but I don't remember the resolution they used and whether it would be sufficient, whether it would be or was sufficient to resolve disks.
Mm-hmm.
Yeah, and I think even then we're still a long way off a general solution that we can just apply.
Yeah. Also, one thing that might be an issue is that the inner binary gets an inclination, and
Yeah,
then it will do this, and then how does this accrete?
yeah. I guess you could still have a circumbinary disk, and there are observations of warped protoplanetary disks.
Sure. Yeah, but it's going to be very complicated.
Yes, it will be very complicated. The crosshatched one you could probably argue is this dynamical three-body ejection that I mentioned before. Again, it doesn't really matter. And then the final big square is triple common envelope, which takes up twice the space because I think this one is fairly symmetric. And we don't have any treatments of this yet, but hopefully we will soon. Where it seems that the general result will be that you can usually kick one of the stars out and then revert it to a binary common envelope, which we can simulate. I think that's actually all I put in here so far. Yeah, so that's the current state of the code. Things to add, mass transfer and decent treatments of supernovae. I think most of that's probably already in just from the standard binary C stuff. Well, the stuff we had at the beginning. That's really slow. This one, right? Like if you have a supernova that where you lose a lot of mass, then the orbit will spontaneously widen. Oh, it's still going. Wow, Zoom really does eat a lot of memory, doesn't it? Yeah, so I think most of that should be fine.
I think that's doable.
Yeah, the question will be kicks, as always.
Yeah.
So yeah, I think that was all I had to say for now. If anyone has any questions.
Oh, that's great. Thank you.
It's really cool.
Yeah, pretty nice. I did have one question. You said some of this triple interaction stuff is very fast.
Yeah.
Do you compare the dynamical timescale of the star to see whether your tidal interaction really is quicker than the dynamical timescale? I mean, it can't be, presumably.
Oh, so you mean, so say on this one here, if say the dynamical time of the star is wider than this peak?
Yeah.
I don't think it should be. But maybe for cases where you have giants, for example.
So for a red giant, the dynamical time will be about a year.
I mean, the dynamical time is.
Geo would know this, I'm sure. Dynamical time scale of a red giant must be around a year or something.
I mean, the dynamical time is roughly the same as the orbital period at the surface of the star, right? So the binary period is automatically longer than
maybe
that.
Not, maybe it's shorter than that.
And I guess you could, in theory, have a triple that is faster than that. Yeah.
I don't know. It's probably an edge case.
I think. I can't think of a system where that would
that's
be.
The convective turnover time, so it's about the same.
For a giant.
No, Rob, I really don't know.
For a giant branch or AGB.
Either. AGB especially, and the bigger the star, the longer.
Exactly.
So,
Giant branch, I thought it would be less
but
than.
on an AGB, the turnover time is about a year.
Yeah.
And they're going at a fraction of the speed of sound, so it's reasonably half the speed of sound. So it must be about that. So then you've got to be careful because your orbital period may actually be a lot shorter than that.
Yeah.
And your timescales here may also be. So I don't know exactly how that will work.
Yeah, it would be really difficult to come up with a system that does that, just because if you say that the dynamical time is roughly the orbital period at the surface, then the binary period is automatically longer. Is that not true?
No, it's not that difficult. A lot of reasonably close barium stars are in that situation.
Okay.
They're not far off overflowing their Roche. See, that's the thing. But they're the interesting ones because they're the ones that are actually eccentric that shouldn't be, because at that separation they should have circularized, but they haven't.
Yes.
So that's why I'm interested in the triple option to try to pump up the eccentricity. It's another way to do it. I don't know whether that's the answer.
Yeah. Well, I guess when we're doing the triple tidal evolution, we already have it's already taking account of things like the stellar rotation frequency and that kind of stuff. So we can just sort of directly to it.
That's true. So there are limits put in the tidal prescription at the moment, so that the tides can't act faster than the convective turnover time in a red giant, which is essentially the same. So we need something like that. But that's very easy to put in.
Yeah. I think it might actually have already.
Yeah, it might also.
Just work with what I've got.
What are your first plans to go and study with
I think, well, I think this will come down to time constraints. When the code is sort of ready to use, I like the idea of doing population synthesis, but I don't think that's at all feasible at the moment. So I think it would be interesting to do a study of how strong some of these various effects are. So, for example, in the paper for Jan's triple tides, he estimates that it's valid in some percentage of triple systems. I think it's like 1 or 2%. I think that would be quite interesting to test and see what the effect of that actually is. We could do the same for some of the mass transfer cases as well, I guess. The three-body dynamics has been reasonably well studied, especially with all these gravitational wave merger events.
Do you know how this compares to the solution that Sylvia has? Because
Yeah, so I haven't looked very much at TRESS generally. So TRESS is an existing triple star evolution code. Sylvia Turnen. Yeah, so part of this was I didn't want to sort of try and end up subconsciously copying what TRESS does. I wanted to sort of look through the things and decide what, how we should treat things impartially. Yeah, I definitely plan on comparing them at some point. Yeah, and the nice thing about this is I know TRESS is part of Amuse, right?
Yes.
But the nice thing about this is sort of similarly it will inherit all the future stuff that goes into binary C.
Yeah.
Which is, yeah, that's quite nice.
What I know is that they have, if there is a mass transfer phase, they just stop the whole thing.
I know they don't do mass transfer.
So they can find the situations in which it starts. And then stop it.
Yeah, I think there are plenty. I think we'll have to do a similar thing for some of the mass transfer cases. But I think there are some you can treat reasonably.
Have you found any distributions already?
I haven't looked very much. I know there is some, but there aren't very many generally.
So I'm wondering if the Moe is the final paper or something.
Yes, I believe so.
They do have information about how many stars are in triples or quadruples or higher order systems, but
yeah, I'm not sure we really have particularly robust statistics over decent mass ranges. I think at the moment, I could be wrong.
So do you track, like, for example, the formation of bootstrap, or is there something that could happen in triple systems?
Yeah, that would definitely be doable.
Because they say that people claim that triple stars would make bootstrappers quite easily.
Yeah, so that's the thing. That's one of the things where it's important to get these eccentricity variations right for, because I think it's fair to say that the main departure from between triple stars and binaries is that in triples it's much easier to get a very eccentric binary, and if you have an eccentric binary, you can do mass transfer, you can do tides, you can do Rashlev overflow, you can increase the frequency of all of these things. So I think that's a solid basis for saying that you expect decent fractions of interacting binaries to be in triples. What the fraction is, I don't know.
So, okay. Well, can you give us that answer? So.
Another quick question. In, for example, M-body 6, there's the KS regularization in which they treat only binary systems, but how is the situation with triple systems in those things, and can this, for example, help there?
I am really not sure, I'm afraid. I haven't really looked into any of the integration with M-body.
Do you know
Any
about this
idea?
one?
No.
No, I don't know how they do it in detail.
So if this could also be, open up for with an API, then that would be a very interesting thing for an embody serving code.
Well, I know that Sarah wants to implement our updated stellar evolution library when we've got that working. So that would be good.
Sure, you should. I've been advised against it by Max. So if you want to open the code, we'll look. But
I will just give them access through the API.
yes,
I have,
And
no,
that's
I have no
the
plan on actually implementing it myself.
Oh, no.
That's their problem.
I know. But I don't know if the code has API endpoints to call it. Binary C does, but embody 6 does.
They can just call it through our shared library. That's fine.
Yes.